This takes us to a little bit of a sidestep, but then again, not really. Because what we actually did now was something very closely related to what people in the chemistry lab or physics lab might call thinking and handling the so-called propagation of error issue. We did actually something a bit more, but it was part of it. Because if I run back, this question, what is the standard deviation in the errors, in the area, sorry, in the function here from time to time? That is, I know what the variability is for x, or the error if you want, if you use that terminology, and I will know what the variability is for the y, or the error. How do they propagate through this nonlinear computation to the x times y computation? This is the same question here with the standard deviation. So that was actually part of it. So I gave you simulation tools. I'm going to give it more formal in a second. For something that you may find analytical, or at least approximative analytical mathematical tools. And here it is. Looks complicated, but it's not too bad actually, if you think about it. And I'm sure for some it doesn't look complicated. For some, I'm sure it does look complicated. I am trying to phrase the question that I was just getting at. Here is the general mathematical expression of that question. I am in a situation where I'm computing some function of a number of inputs. Now it could actually be n instead of just 2. Before it was 2, x and y, now I could have n of them. And I'm considering any nonlinear function of those ones. I would like to have a way to find the variance of such a nonlinear computation of a number of inputs. It's a pretty ambitious goal to be able to find that. I call it, this is the name of it, this is the other way of defining what it is. So that's the concept, and of course that's the first thing to realize here, to actually understand that that's what the question is about, related to what I discussed. And maybe you need to sleep on that, but here it is. Now, we actually know something already. Maybe we didn't put it exactly like this back a few weeks ago when I gave you the variance rules. I think actually Peter was here to do those particular ones with you. Those were the rules that told us that if the construct we're interested in actually is a linear combination of the original random inputs, then I know what the variance of this new construct is, because it's the linear combination like that. It's the sum of the combinations of the coefficients squared times the original variances. That's a variance rule that you were given back in chapter 3, right? So this is a version of the rule, but now I'm more ambitious. I'm not only talking about linear functions. I want a formula for any kind of nonlinear function. It's a really big step. And it's impossible to do it analytically, exactly. But you can do it approximately. Basically a Taylor expansion, like this, that tells you, and this is the classical independent error propagation rules that you might meet in chemistry or physics or somewhere, that the variance of a nonlinear function is again, and look at the similarity of the formulas here, it's again the sum of the individual variances of the x's in a way. But instead of just plugging in the square of the coefficients in a linear thing, the things that I put in is the square of the derivatives of each one. Did you recognize that word? Derivative. Sorry for trying to be funny in a, I don't know the English word for what I'm doing, so that's good. I would know a Danish, I would throw in the face of someone who's doing something like that on me, but here I did it. Sorry, I'm getting old and tired. But God damn it, I saw the results on the exam exercises where I ask you to find a derivative of a simple function. Hey, you were taught derivatives of simple functions in high school. You were taught that for a reason. You were taught that because they are used in life. And then you signed up for an engineering school, and I guarantee you derivatives are used by most engineers. So here we are. You also need them in stats. Sorry. So you need to remember the derivatives of simple functions to be able to work with this. How should we use it? Well, we want to find the variance of a specific measurement. It's a little bit special terminology and a way to put it here, but it resembles a bit of how you might put it in kind of a lab report in physics or chemistry, where you actually did some measurements and you want to relate to the error of what you do. So I want you to use this error propagation law to solve that question. And here are the results. To use it, I need the variances of each individual input. You need to read the situation and identify those ones. Those were given in the text. Then you need to identify the function that we're working with. That's the product of x times y. Then you need to do the partial derivatives. So I do the derivative of this function with respect to y, with respect to x. First, let's begin there. With respect to x, the y is the constant. With respect to y, the x is the constant. So that's the most simple derivative rules we can find. So the result of this question becomes the two individual variances times those derivatives, which I plug in here. And then to actually get a number for those derivatives, it's the square of the derivatives. By definition of the formula, the square of the derivative is used. I plug in the actual measurements as an approximation of where we are, and we get, in this case, a result, theoretically, that is like this. So this is the mathematical way of doing what I just did simulation-based a few minutes ago. It's actually solvable here. There is a rule, an approximative rule, that could at least give us the standard deviation or the variance of the product of two things by this approximate rule here. The rule is part of the syllabus, as I indicate. That was a method box. Now, I give you the method box that actually corresponds to what I already exemplified in the area example. We're going to see a few method boxes today of this type. These are simulation method boxes. So they're a bit different from what you've seen. There are no, in this case, there are even a single formula, but most of the time there's no really formulas. There's just a procedure. It's almost like a symbolic software program, right, that tells you what to do to make it happen. Simulation-based tools are doing it in the computer. It's not mathematical analytical formulas. So here's the formal method box, doing what I just did, putting into words what I just did. If I have some measurements, and I know what those variances are, then I simulate. And I make the additional assumption about the normality for this version of the rule. I simulate from the normal, each individual normal distribution. I did that for the length and the width separately, right? I simulate each of them using the variances that I know. Then I compute the function all the 1,000, 10,000, 100,000 times. And I compute the standard deviation of those simulated areas, or in general simulated function values that I give you here. So this is just the SD computation in my simulation example of the area that I have formulated more generally here. That's error propagation by simulation. So two similar tools, the mathematical approximation and the simulation-based tool for the same thing. Let's look at the clock. We have a few minutes for this one. Actually, I told you you should take a full probability class to solve the issue. Well, for the variance, we could maybe just take a minor class and then we could solve it. For my question about the percentage of going above 0.1, I couldn't answer it without the probability class, but I could actually mathematically, by one or two rules more than you already knew, you need a couple of extra rules compared to what I taught you. You could actually deduce what the variance. I'm not going to take us through this. This is not itself is not so interesting step by step. It's just to show you that it could be solved mathematically, analytically here, not only approximately but exactly. And the nice thing about this exact computation, which you don't need to be able to follow, is that you will realize that this exact computation actually contains the approximate part from before as a part of it, and then a little bit extra, which makes it exact, but shows the difference between a Taylor approximation and the exact number. Anyway, it's just to show you it could be done here without rocket science. But a little bit more than we have in our class would be needed. So, to sum up about the error propagation and intro to simulation, but the title just now is error propagation, which in a way is, as I said, it's a bit of a sidestep. But then again, it's an important sidestep, and if you really would be a bit generally minded here, you could say that all statistics is really about is error propagation. I mean, everything you would be taught in this course and the rest of, you could have 20 courses at this university in statistics of, all of it is some kind of error propagation. Some of it might be a bit more predictive if you go to the machine learning areas of it, but a lot of it is about errors and how they propagate through nonlinear systems. Not every high school teacher in chemistry, physics, biology realizes this link between lab work, uncertainties, error propagation, and basic statistics. And I think I'm not getting fired if I claim, because I did previously. And I'm sure not all university teachers in chemistry, biology, physics, environmental stuff, whatever we teach at this brilliant university, these insights and connections about basic statistics, uncertainties, and sort of lab numbers and uncertainty error propagation, well, you won't. There's basically no one is as wise as I am, right? So don't expect to meet this. Well, there are a few, but they're not in. I should stop now. I'm just trying to preach a little bit here, and this is my little way of trying to change the world. We need to change this. We're trying to change it in the elementary schools, high schools, but we're going to change it at university also. We need better integration. We need higher understanding from your teachers in all the other classes of this link between uncertainty and numbers. And yeah, let's try to change it. If they don't do it properly, let them know, right? Send them to me. And I'll teach them. Back to business, error propagation. I was just to say it's a pretty general thing actually we're talking about. Almost everything. I've given you 3 different approaches for this error propagation thing. I've given you the simulation-based approach. We started that as an example, and then I gave you the formal method at the end. I gave you the theoretical derivation just as a illustration that it could be done, because I expect you to be able to work with that. And then I gave you the error propagation approximate. It's only an approximate tool. It's a nice tool, but it may or may not be exact, depending on the situation. And the simulation approach does offer a number of advantages. it actually is not an approximate tool in terms of the nonlinearity. It does offer a way to actually try to think about, now I gave you the method only as a normal based method, but it doesn't take that big of thinking to say I could exchange the normal assumption for assuming any other distribution and do the same thing. So I could actually assume other distributions than the normal and do error propagation with all sorts of nasty distributions. And we could compute basically anything. And what's the limitation then? Because nothing grows all the way up. Few things do. Well, the limitation is that it was mentioned, well, we have to assume some distribution to do it, some probability distribution, and that assumption may go wrong on us. And then it may fail, right? I mean, nothing is, but if you think your assumption about the world is okay, it's a really, really strong method. That's looking into errors by simulation and by exact method. We need to do the game before the break. Whoa. Don't worry, I won't shout at you now. I did my shouting for this day. Not too bad in 30 seconds. Not perfect either. But yeah, I pushed you there. I pushed you, I know. And I'm pushing you a little bit here because I know that for some of you, this is not everyday business to go around and do partial derivatives. I mean, we're a diverse audience here. For some of you, it's a piece of cake because that's who you are. For others of you, it's less of a piece of cake. And I'm trying to push you to think about this, right? We must be able to deal with those basic stuffs also in a class like this. That's just how it is. Even though it's not really part of this course, it's part of the toolbox of our basic math skills. So, who are on the top? That's me. That's good. Let's break. 15 minutes.